Okay, welcome back. So the idea with templates is really to give us more flexibility with our classes. Because for example, if we think about things like the vector class, right, if it wasn't a templated class, then we wouldn't be able to choose the types of the objects that are in the vector, right? So we know that a vector itself is really an array that's dynamically managed, right? But we also have control over the types of elements that are stored in that vector. You know, a vector of integers, vector of chars, vector of doubles, or even a vector of a class type, such as a vector of coordinate objects or employee objects, right? Or so on and so forth. And then we also have things like the string class, right, which is also a built-in class. But when we create a string, right, there is no angular brackets with the type, because a string only stores characters, right? It's like a vector, but only stores type char values. But in some cases, right, we do want to have some degree of control over the types, right, that are going to be used. And so, one way of handling that would potentially be to create different versions of a class, with slightly different names, for example, and then have one that deals with, integers, maybe one that deals with chars, or we can take advantage of what are called templates, which kind of makes that whole process a lot more convenient and straightforward. So instead of creating separate versions of classes, ourselves, we can create one templated version. And then the idea is, if we make a templated class, then, like, for example, think about a vector, right? You make a declaration vector int or vector double. So when you create an object of a certain type, right, it creates that version of the class, right? So you have kind of a generally defined vector class as a templated class. But then when you start creating specific objects of a type, right, it's going to create those specific versions, right? So one way we can almost think of it as kind of like a stencil. You have this thing that's called a template, which is very generically defined, right? But then you can create actual real different versions of the class with, actual real types. So when you create the objects, that's when that version of the class would be created, right, with that particular type. And so just in the same way that, things like the vector class or the DQ class, which we'll look at throughout chapter 15, just in the same way that those classes are templated, those are classes from the standard library, right? But we can also make custom classes that we've defined ourselves, right, to be templated, or a function can also be templated as well. So that way, again, we can write out one version of a function, and because maybe that function is going to do the same general kind of things regardless of what type of data value we're working with. And so rather than having to explicitly write out, different overloaded versions, we can have one templated version, right, of the class. And now, of course, the idea is that there is some close relationship, right, between templating and overloading, because overloading, right, is something that, we talked about before with functions. And, certainly it's possible to write out different versions of a function with different types, but the idea is templating is another way of approaching that. And perhaps in some cases, right, a more convenient way, because it means we only have to potentially write out one version of the function in this case, or the class, and then the compiler will handle all the details as far as generating the different versions based on what actually happens in the program. So we have one template definition, right, of either a class or maybe a function. But then as we start creating objects, or as we start calling a templated function, right, we can end up creating different versions, right, along the way of that thing that we're templating. So again, it's very convenient. It's very powerful, and so we'll see that as far as setting it up. So we'll look at examples where the the implementation is going to also be in the header file because it gets a little bit more involved and complicated with templates trying to do it all in separate files. So we'll see examples where it's going to be in the header file when we're making the class templated. But in terms of syntax, we start off with the word template. And then in the angular brackets, we can put in either the name type name or class, and then we have an identifier name. And you'll see examples where we might just use the letter T for the identifier name, but that T represents an actual type, like a real concrete type that eventually you're going to actually use to create the object, right? Because of course, if we're talking about creating a class object, at some point we have to actually talk about a real concrete type, right? So the template itself is a, sort of a generic abstract concept, right? We have an object or we have a class of template type T, and that type T is used throughout, the various functions and member variables and so forth in the class, but T is going to be replaced by an actual real type, right? Either a primitive type like integer, for example, or char, or a non-primitive type like a coordinate object, for example, or a string object. But it's going to have to be replaced by some sort of real actual type, right, eventually. And so that's going to happen when we create objects using the templated class, or when we do a function call, right, for a templated function. But in terms of syntax, right, that's all we have to do to really, as a starting point here, is, and we'll see in a moment with the code example, but the word template, right, and then we have the angular brackets, and then we can say either the word type name or class, so those are interchangeable. And then after that, after the word class or type name, is just some sort of identifier. And again, sometimes we might just call it T because that stands for the word type, which is what T is going to be replaced by. Now, eventually we'll look at things like what are called non-type parameters, meaning when you might have, because this comes up as well with some types of classes, such as the array class container. You can also have, so you can have several different things, right? You can have, for example, multiple different types parameters in your template definition. So meaning that potentially pass in multiple different types, if that might make sense based on the way the class works. You can also have what are called non-type parameters, meaning parameters in your template definition that are not types, but rather values. And so that comes up especially with things like the array class container. So meaning not a built-in array, but the actual array class, which is part of the standard library in C++. It's a little bit different than vector, right? Because with vector, at a minimum, right, with vector, you only have to put one thing inside the brackets, right, which is the type, because vector is dynamic and the size can change. But with an array class object, you also specify the size of the object as well, meaning in those angular brackets. So like you create an array object, right, it'd be array angular bracket int comma 5, and then after the angular bracket, you put the name of the array. So that's an example of what we mean by a non-type parameter, because the first parameter in the angular brackets would be a type like integer, and then the second one is a value like the number 5, which represents the size of that array object, right? Because unlike a vector, an array object is not going to change in size ever, right? So we have to commit to one specific size, whereas a vector can change. Well, yeah, can there be template objects or just class? They go hand in hand, because if the class is templated, then the corresponding object is also going to be in line with that, meaning the object is going to be templated, because it's going to have to be, right? Now, it is possible also to apply the concept of default arguments to a templated, for example, class or templated function. So like if you don't, you can potentially set it up that way where if you don't pass in anything, then there's going to be like a default type that's used. But they go hand in hand, right? So if the class is templated, then the object, right, really is templated as well. Whereas if if the class is not templated, like for example, the chord class that we did back in chapter 10, um, because what we did there is we had the two member variables of type int, right, for X and Y. So that can't be changed, right, when we create a chord object, because it was not a templated class. So things like the value, the types of X and Y are always going to be ints with the way that we set up the chord class. Whereas with a templated class, if the class is templated, then the object, right, is also really going to be templated as well. Meaning that either you're going to have to specify, a type yourself, right, when you create the object, or perhaps the class might be set up in such a way that there's a default type, and to where if you don't specify that, then it just would apply the default type. But usually when we're creating an object with a templated class, we do, want to put that type in there specifically. So everything, goes hand in hand, right? So templated class and templated object, right? Those really go hand in hand together. As far as functions, what we'll see really is that when you make a class templated, that same identifier name, so you might call it T, for example, can be used throughout the whole class definition. So you can use it with your functions, you can use it with your member variables, but sometimes we might also want to take a non-member function, meaning, for example, some random function we might have, in the application program, and make it templated. So that kind of thing is also possible. Mm-hmm. But yeah, so templated class and templated object, right? We really want to think of those as having a correspondence with each other, right? So they they go hand in hand with each other. And so we'll look at an example here of a class called stack. Now there's also a built-in stack class, but this is a manual implementation of stack, just kind of a short version of it. But it shows the basic idea of templating a class, as far as writing out the template declaration and then using that type throughout the class definition, right? The class body. And so the idea, and we hit on some of these points more, especially throughout chapter 15, right? So templates are from chapter 18, and then container classes are in chapter 15. But so the idea is that, when you think about a stack is really a concept, right? There's different ways that we can implement in general the idea of a stack, right? Because a stack is a last in, first out type of data structure. So, you think about things like, if you finish dinner and there's several plates that need to be washed and you stack them all together, well, you're going to take, right, the plate at the top of the stack and you're going to wash that first. And that plate, right, was also the one that was added the most recently. And then the last plate that you're going to wash, right, is the one that you added first to the stack or to the pile. But when we talk about a stack, right, what we're really talking about is using the structure in a very specific, limited way, right, regardless of how it's actually implemented. And that's kind of the whole big point about chapter 15 and what we call container classes, right? But so in general, there's different ways that we can implement a stack. You could implement it with something like a vector, for example, or a DQ, as we'll see in this example, which is somewhat like a vector, but we'll really see the difference between a DQ and a vector, especially in chapter 15. But a DQ like a vector is also like an array, right? The elements are stored, we can think of it at least conceptually as being stored together in memory. Now, we'll see throughout chapter 15 that some things actually do store all the elements together in memory in one big block, like an array object or a vector object, whereas a DQ is a little bit different, right? We'll see that it's kind of almost semi-contiguous, but the elements are not all stored together in one big block. But the idea is we can take a concept like a stack, right, and we can implement it really several different ways. But the point is, if we're truly treating it as a stack, then we're not just going to go to some random location within the structure and access it, right? We're only going to be accessing the top, right? Because that's exactly what we mean by a stack, right? And what we mean by a last in, first out type structure. So a stack is just, right, a restricted usage of a structure, regardless of how it's actually implemented. But we'll look at a case where it's going to be implemented with what's called a DQ, which is sort of kind of like a vector, but there are differences in terms of how it's, you know, physically implemented in memory. So we'll implement it in terms of a DQ or double-ended queue. But in terms of how we actually use the stack, right, we're going to be doing things like push and pop operations. So we can always push a new element onto the top of the stack. We can pop and remove an element from the top of the stack. And we also have a function that will return the value of whatever is currently located at the top of the stack. But we're not going to be going to some other random location within the structure, right, that's not the top and accessing that, right? Because we're acting as though it really is a stack. But the idea is this class, this stack class, is also going to be a templated class, which gives us that flexibility, right? Because now, you know, we're not limited to just something like, well, I can have a stack of integers, but that's all I can store are integers on the stack. Because we're going to be able to store really anything, right? It doesn't necessarily have to be, you know, an integer or a double. It could be whatever type we want, because a stack, right, is a very general concept, and we can have a stack of different types of values. And so one way of handling that would be to make the class itself a templated class. And then we'll eventually look at an example where we can also do things like take a standalone, like for example, non-member function, and then make it templated as well, because, you know, sometimes that's going to be very convenient too. But we'll look at the stat class again. It's not very long really, because it just kind of has a few basic operations. You know, kind of the common ones like push and pop, top, and then, you know, a few others that we'll see. It's actually pretty short, right, in terms of the class code, but we'll see the basic idea in terms of the actual syntax for making the class a templated class. Because this idea of templating is going to come up right in chapter 15, because when we talk about these container classes like vector, DQ, you know, list, forward list, array, which we'll see in chapter 15, we call those sequence containers, but they're all examples of templated classes, which means they have that flexibility of not being locked into or committed to one type, but rather they can work with any type of type that we might throw at it, right, when we create the object. All right, so let's look here first at this stack class. Now, in this case, we only ended up needing one template parameter. So the syntax here is the word template, right, written out. And then we have these angular brackets. And then we have the word type name. And then what comes after T, or what comes after type name, is really up, you know, to us as the programmer, but we're just using T here. But that T is going to be replaced by an actual real type. So that's the template declaration, right? Just in this case, again, just the word template. This part here can be either the word type name or the word class. So those are interchangeable, right? Type name or class. And then after that is the type. So we would also call that a type parameter, right? Because it is going to be, T is going to be replaced by an actual real, you know, concrete type. And then this, the other thing is that we're implementing this stack in terms of a DQ, which is commonly how a stack might actually be implemented. We'll see in chapter 15 how it's different than a vector, but so we did the include DQ there. and it doesn't have to be T for the identifier name, but we're just using T for the word type here, really. So template type name T, and then the idea is we're going to be using that T throughout the implementation of this stack class. So where we would normally be putting in a type directly, like maybe integer, for example, instead of doing that, we're using T, because T is going to be replaced by an actual real, right, an actual real object with a real concrete type. So T here, for example, this function top, what it's supposed to do is just return the top element from this stack. Now, again, it's actually implemented physically as what's called a DQ, or a double-ended queue, which is somewhat like a vector. And in the DQ class, we have a function called front, which will return the front, or the first element. And then we also have a function back that'll return the back element. So the idea is that the front of the DQ is what we consider the top. So to actually return the top element, what we do is in the underlying DQ object, right, we just say return the front element from the DQ. So return stack, and because we'll see down here that stack is the name of the member variable. So meaning uppercase stack here with uppercase S is the name of the class, right? And then the member variable is stack with a lowercase s. And the type, you'll notice here, the type of the member variable is, it's a DQ object, right? So similar to vector, we have the word DQ and then the angular brackets, but then you'll notice that that T from the template is in the brackets instead of a concrete type like integer, because T is going to be replaced by an actual type, right, when we create objects of this class. So every stack object is going to be implemented as a DQ, right? That's what we're trying to say here. That's the underlying implementation of the stack, is this DQ, or double-ended queue. But the idea is that the front, right, the front element, or the first element of the DQ is what we consider to be the top, right? That's the way our implementation works here. So when we call the top function, it's going to return back to us the value that's at the top. So the whole idea with the stack, right, is you're limiting access, right? So even though it's implemented in terms of a DQ, right, and with a DQ, you have the ability, like an array or a vector, to access any random location, right, using, for example, brackets or pointer notation. But we're restricting that, right? Because if you allow that, then it's no longer really a stack, right? If you can just go to any random location and do whatever you want, then it's no longer really a stack at that point, right? So for it to truly be a stack, the only element we should be able to directly access is the top element, which is why we have, again, a very limited set of functions here, right? We don't have functions that allow, for example, direct access to some random index I. But what we can do is access the top element. So what this does is it returns stack.front, the first element in the DQ, which is what we consider to be the top of our stack conceptually, right? Now, the return type here, you'll notice, involves T, right? The same T from here. But notice that we said const T ampersand, meaning, and again, T could be integer, it could be char, it just depends on how we create the object. But so in other words, we're returning it by reference, but by constant reference. And the idea is that we don't really want the return value to be, we don't want to be able to use that to change, right, the actual element at the top. Because again, we have to take into account what we're doing here. So T is the same T that's going to be used here, right? Just referring to the type, right? The actual type of values that are stored in the DQ, which is the underlying implementation of the stack, right? But if we're returning it as a reference, type, and we don't make it const, then it would be possible, to use that return type to, for example, change the element at the top, right, without going through, for example, the push function. So what we're saying here again is that everything should be very tightly controlled and restricted. So the only way that you should be able to change data values on the stack is through the push and pop functions, right? We shouldn't be able to do things like, call top and then use the reference returned by top to, change the value at the top of the stack, kind of like the issue of dangerous reference return and dangerous pointer return that we talked about back in chapter 9. So, but if we make the return type constant, then we're okay, because now, as far as the return type, right, we do return the top element of the stack, meaning from the DQ, we return it by reference, but it's also a constant, so we can't use that return value to change the value that's sitting at the top of the stack, which is a good thing, because we shouldn't be able to do that. Only the push and pop function should be able to actually change the content of the stack, right? Not the top function. So the top function is like read-only access, right? It returns the value of what's at the top so we can see what that value is, but we're not going to be changing it from calling top. So that's the idea with the constant reference return type. We don't want that function to be able to do that, because otherwise we have that situation of a dangerous reference return. But we do have a function called push here. And that function can be used to actually modify the stack, right? To actually push or add a new element onto the top of the stack. But you'll notice that the implementation here is just stack dot push front, because right, that's in line with what we set up here also, because we said that the top of the stack is really the front element or the first element in the DQ structure. So in other words, as far as what it really means to push an element on the stack, it means to add a new element to the front or the beginning of the DQ. So unlike the vector class, which does not have a built-in push front function, right? Because vector only has things like it has push back and pop back, but not push front or pop front. The idea with DQ, and we'll see this more throughout chapter 15, but the idea with DQ is that it's good performance-wise for either insertions at the front or at the back, whereas vector is really only good with insertions at the back, which is also why it doesn't have a built-in push front function, because it doesn't really have good performance for that. But DQ is designed in such a way that it can still have pretty good performance, right? With adding elements at either of the two ends of the array, right? Meaning the front or the back. So in terms of the push function, what we do is we just push, we call the built-in, right? This is the built-in push front function that's in the DQ class. And so that's what we mean by pushing to the stack, right? Just adding a new element to the beginning or to the front of your underlying DQ structure. So just stack dot push front is all we have to do there for the push function. So just pass whatever it is by reference, const reference, and then push it in. The pop function is kind of a similar idea. Since the push function in our stack class works by calling push front in the underlying DQ implementation, pop is just going to go the other way around, right? Pop is going to have to remove that first element, which is what we can currently consider to be the top. So it just does stack dot pop front here, and then there's no parameters, so the template parameter doesn't show up here. But we're already seeing how this is going to work out, because T is used here for the top function, and then it's also used here in the push function as well for the parameter. So T will be replaced by an actual type, such as integer, depending upon what type of stack object we create, for example, in the application program. But that's how pop works, right? Just calls pop front and then remove that front element from the DQ. And then we have this function here called isEmpty. again, that's a good thing to have as well, because we shouldn't be calling, for example, in the underlying DQ, we shouldn't be calling pop front if the DQ itself is already empty. So that's why it's good to also have this empty function. That function can be called at any time to check if the underlying DQ is already empty. So we can check that, for example, before we call pop. And then we have a function here called size, which just returns the size of the stack, meaning the size of the underlying DQ object, which is the stack. And then the member variable, as we saw here, was just an actual DQ object. So again, it's similar kind of declaration to something like a vector, except it's the word DQ right before the brackets instead of the word vector. And then the type goes inside the angular brackets. And again, because this is a templated class, T is what we use here, but T is going to be filled in or stenciled in, so to speak, when we create an actual object, right? Meaning an object of the stack class. So that's the basic idea. Again, it's not a long class, right? But it is showing the basic idea of what it means to implement and how to think about a templated class. And again, it's something that's very useful here, because instead of having to create, separate, maybe different versions of a stat class, one for integers, maybe one for doubles, one for characters, right? We just have one definition that we write out, and the compiler is going to take care of everything else, right? It's just going to go through the process, because really what has to happen, right, kind of like function overloading, is in the end, you're really going to be, in effect, creating different versions of this class, right, based on the objects that you create. But the compiler, right, is going to handle those details instead of us having to handle it ourselves. I'm going to chat here for a moment. Yeah, if this template class is inherited, T will replace with a given. Yeah. Yeah, because it'd be the same idea with like an inheritance type situation. Because I mean, if you created your, for example, derived class object, then you could still apply the idea of a template to that as well. Because if it's inherited and the class is templated, then that part of the object would still be templated. Yeah, so there's in general about inheritance with question about inheritance with templating, and so that's possible, because there's really a lot of things that we can do in general with templates. We can even have, in this case, we only had the one parameter because we didn't really need to have a second one, but we can have multiple parameters. We can have multiple parameters, and certainly, it'd be possible to combine it with things like inheritance. And then in that case, you'd have things like the when you create the derived class object, right? Then yes, if the base class part is templated, then you still have to think about that aspect when you create the derived class object. So yes. Now, of course, one thing we can keep in mind, though, in the big picture here, is that even if the class is templated, that doesn't necessarily mean, right, that that you're restricted to making everything in terms of that template type T. So, and that even came up in this example. But it means that you could still have, like, for example, another member variable that is like an integer, for example, while other things are using T's. So we can really have any type of combination Right, we can have any type of combination that we need. So for example, with the inheritance situation, I mean, you're inheriting from a templated class. So then, I mean, that same type T, could be used in the derived class, but then, it could still work out to where in the derived class, you might have like a specific member variable that's always an integer or something like that. So you can still do that, right? You can still refer to concrete, right, or specific types, even if you're templating the class, right? So you don't necessarily, in other words, have to use T for everything. It just depends on what you're trying to accomplish, right? What you're trying to do. Going back to the code here. Yeah, and we even saw a little bit of that here too, because like for example, bool, we use bool for return type, or the size T for return type. So there are cases where we're still referring to things other than T, but we're using T where we really do need to use it, which was the variable declaration, and a couple of the functions, right? The top, along with the push function. And then the application program, the idea is that we're just kind of testing this basic idea out. And so what's happening here in the app program is we're creating a stack object here. And now, but because this is a templated class now, we think about creating this in a similar way to how you would think about creating a vector object, meaning that there's a type here always in the angular brackets, right? So the word stack, and then in this case double, and then we gave it the name double stack. And then here the idea is, again, we're just wanting to add some elements to the stack, and then be able to do things like print it out. So we create the stack object here, a stack of doubles in the beginning. And then the size here that we want is going to be 5. And then so we loop through, because the stack is initially empty, right? Meaning the DQ that the stack is based on is empty, because we can have, similar to vectors, a DQ can be empty at the beginning. But then the way that we build up the stack is we call that push function that we implemented, right, with double stack, our object. And then that in turn calls, as we saw, the push front function for the underlying DQ. And then we print it out. And then the way that we're changing this, again, just as kind of a short example here, we're just adding this value 1.1 to it, right? So that way each time we have a different value that we're actually pushing onto the stack. And then we have another follow-up loop here. And this is where we're using that, where we're taking advantage of that empty function, or that is empty function. Because in this case, instead of using a for loop, we're just using a while loop with that empty function. And because we said that in general, when you're popping, it's good to check things like empty, to make sure that you never call pop on a DQ, in this case, that's already empty. But see, we print out the top element by calling the top function. And then we turn around and we call the pop function to actually remove it from the DQ physically by calling the pop front function for the DQ. So we build up the stack with the first loop, right, with the stack of doubles in the first loop, and then we tear it down, or we destroy it through the second loop here. And then the idea is, next we do almost the same thing again, basically, but now it's with a stack of integers instead of a stack of double values. So whereas here we said stack double, and then the name double stack, this time we said stack and then int as the type inside the brackets. And then the name there was int stack. And in a similar manner, the first loop here is going to build up the stack by calling the push function, but in this case it's integers rather than doubles that we're pushing. So, and initially we put 1, as the value of int value, and then we increment that each time, right? So that way we have a different value that we're pushing on each loop iteration. But we build up the stack here with this loop, and then once again we tear down or destroy the stack with this pop loop. And so what's going to end up really happening in this case is somewhat similar to how we think about function overloading, right? And so, right, we're really doing what you can all think of as class overloading then, because we think of it as, you know, one stat class, right, that was defined generically, right? So when we talk about templates, right, it allows us to do things in sort of a very generic kind of way, where we're not really being specific at all, right? Because of course we can't talk about T, but we can think about what T is going to be actually replaced by. So that happens when the object is created, right? So when you first create this object, right, stack, double stack, double gets sent in, right, you know, to T here. And so what really happens is we create a version of the stack class where T has been replaced by double. So meaning everywhere within here, right, T has been replaced with double. And likewise, when we create the second object, right, at that point, we now have created another, right, another separate version of the stack class where T has been replaced by integer. So now we've really stenciled out, kind of like stenciling, right? We've stenciled out two different versions of this class. And, you know, if we kept going and you know, did stack char or something, then that would be a third version. But rather than having to always define all those separately ourselves, which is, you know, not really convenient trying to account for every possible type that you might want to use, we define one templated version, and then the compiler can handle the details as far as stenciling out, right, different versions based on the objects that you're creating here. So in this case, we're going to stencil out, right, you know, two different versions of the stack class, because one stencil, if you want to call it that, is going to be with type double, and then the other thing that we stencil out is a version with type int. So two different versions of the stack class, right, that are going to automatically be created through this whole process, of templating. So again, we're seeing that it's very powerful, right, and in terms of, you know, the things the compiler is doing for you, really, that you don't have to do yourself. And it's also very useful because, I mean, we know that the stack is always going to work the same way in a general sense, right, regardless of what the types are. You know, push means the same thing regardless of whether you're pushing a char or an integer or a double, right? Pop means the same thing. So of course it's more convenient to not have to define that separately, right, for every single possible thing that you might want to do. And especially when you think about even things like, you know, where the type here may not even be a primitive type, right? It could even be like a chord object, right? So we can start to see quickly why it's so convenient, because we don't have to try and think of any possible situation that might come up, right? This templated class is geared really to work with whatever type, right, that we might want to use here. So we have, in general, right, a very generic stack class that can be a stack of anything. And that's exactly what we wanted here. But in this case, with this application program, we only created two different types of stack objects, one of type double, and then one a little bit later of type integer. So we just want to keep in mind that that's happening, right? It's actually creating because the templated, you know, the templated class itself is it's not concrete, right? Kind of like how we talked about abstract classes and polymorphism. It's sort of a very generic concept, right? But what is T? Well, T is an actual real type at some point. So, but that happens when we start creating objects, right? So this is going to create the first version of the stat class, or stencil out the first version where T is going to be, all occurrences of T are going to be replaced by, by the type double here. And then likewise, when we later create the second one, which that was down here, this is now going to create or stencil out the second version of the stat class. In this case, all occurrences of T, right? Everywhere that we use T in the class is just going to be replaced by int. And then we, again, as we saw, we just do the same push loop and pop loop that we did with the double stack. So again, just a short application program in this case, but it's going to be pushing some elements and then printing them out and then popping them back off the stack. Okay, so here we have, at the beginning, we have, okay, so pushing elements onto, onto double stack. And then we started off with the value 1.1. And then on each loop iteration, we added 1.1 to the current value. So it's going up in that way. But we have 1.1, 2.2, 3.3, 4.4, 5.5. And then when we hit the corresponding pop loop, now we're popping everything off the stack, right? So in that loop, we called the top function. That was the loop where we called the top function, return the top element, which is the element that's actually at the front of the DQ structure, print it out, and then pop it by calling the pop function, which in turn calls the pop front function for the DQ object. So we just pop everything off, right, in the reverse order that we pushed it on, right? Because we know that the stack is a LIFO, or last in, first out type of data structure. So now in the pop loop, we get 5.5, 4.4, 3.3, 2.2, 1.1. And then in the next block, where we're dealing with the stack of integer values, we have the values 1 through 10, right, which we pushed onto the integer stack in that order. And then we have the corresponding pop loop where we pop them off also in reverse order. So 10, 9, 8, 7, all the way down to 1. So that's the basic idea of templating our class here. Short example, but what we're going to see is that this is, again, something that's very powerful and very convenient here. And the container classes that we'll be looking at throughout chapter 15, meaning the built-in container classes like DQ and list and vector, for example, they're all templated classes for that reason. So that way we can have, a vector of whatever elements, or a list with whatever types of elements, or a DQ with whatever types of elements. So again, it's a lot of, it's very powerful. And we saw that it really didn't take a lot to actually set it up, right? Just start with that template declaration, and then we just use that identifier as needed throughout the body of that class definition. So that's what we mean by how the replacement works. So again, when we do the first object here, we know that double, in terms of the class, right, double is going to go and replace t here. So then, for example, when we're working with the double object and we think about the call to top, right, the return type at that point really is const double ampersand, right? And then the type for the parameter for push is const double ampersand. So of course, when you're working with the actual object, right, everything is going to be done concretely. So t is going to always be replaced by t is also going to always be replaced by the actual type. So, and when we create the integer stack object, similar idea, right? Int is going to replace t up here, and then also every occurrence of t throughout, right, the body here. So for example, when we use integer, then the stack object that we create is a deque of type int. And then also the return type of top would be const int ampersand. And then push, likewise, the parameter would be const int ampersand. And then that function can also be const as well. But that's the idea with templating the class. And again, what we also saw, which was convenient here too, was that this T that we had in the template declaration, above the class definition, was that the T could be used everywhere. So it's used both, for example, in some of the functions, and it also was used for the type of the member variable. So in that sense, right, we only had to have, there's only one template definition above the class definition, and it was just used for everything as needed throughout the entire implementation here. And then again, going back to the earlier point, we can also use the word class there. So either type name or class can be used as what we put before the identifier, meaning what we put in this case before T. So those two are interchangeable. But that's the idea of what it's going to look like syntax-wise to set up a basic templated class. But we'll also look at an example with a standalone function that's going to be templated. And it'll be similar to what we did here, right? Same type of template declaration above the function, but whereas this is templating, right, the entire stack class, we'll also look at a case of where just a single standalone function is being templated. And again, sometimes that comes up as well because you might have in your application program, right, which works with the templated class, a function that would also be convenient to template, right? Similar to how templating the class itself, right, was convenient. So we'll see that in the next example. Okay, so this version, same stack class, but a little bit of a different app program. So whereas before we were doing everything in the application program before was in main, here we actually have another function in the application program also. So we, for example, create this object another stack double object, and then, but then we call this function test stack with that object, and then we create an integer stack integer object, and then pass that to the test stack function. And that function, right, you'll notice that we're calling it with both types, right, both types of stack objects, but it's also a templated function. So here above the, in this case, above just the function, right? Because this is function templating. We're just, in this case, we're just templating a standalone function, whereas before we were templating an entire class. But so we have, again, the template, either the word type name or class, and then the identifier, which again can be T here if we want. And then this is the function. So we're doing the same kind of thing we were doing with the last version of this stack class. It's just now, instead of doing it all in main, we have another function doing the majority of the work, right? As we often do. But we templated that function, so that way we only have to write out one test stack function, which will work with any type of stack object that we might pass to it. So rather than, manually overloading different versions of test stack, one that takes in a stack of integers, one that takes in a stack of doubles, and so on and so forth, we just can have one templated version. And just in the same way that the class gets stenciled out, right? You stencil out different versions of the class, right? Where you have a stack of integers or a stack of doubles or a stack of chars. You can also template out that, that function, that standalone function, different versions of it. So stencil out a version of the test stack function where T is replaced by int, right? So a stack of integers. Stencil out a version of test stack where T is replaced by double, and so you have a stack of doubles. So we're just applying the exact same concept to templating, but now we're applying it to a standalone function as opposed to the class, but it's in many ways the same general idea. So return type here is void. Name of the function is test stack. And then these are, first thing here is the parameters, right, that we're passing. So let's look at our, because there were several things, if you look at that function call or both of the function calls from main, right, there's several things, that we're passing in. One is, the first parameter is the stack object itself, right? We're passing that stack object by reference. So stack T ampersand, return to our type of the parameter, where T is going to be replaced by an actual type when we call the function. And then that, again, that type T is used several places throughout, right? So for example, if this is a stack of integers, then the type of the value that you're going to add is also type int. And then the amount that you increment by is also that same type. And then we have the size, right? And then we do things like the pushing, right? So we have that same kind of push loop here. And then the last parameter is a string with the stack name. So we can distinguish the two function calls as well. But then here we start building up our loop. So, and again, that's much is similar to what we did before. So we have that push loop here, where we call the push function, print the value out, and then we increment it using the increment value like we did before. And then we have the pop loop that loops using the empty function. And each iteration we call the top function, and then the pop function to actually remove it. But whereas before, when we were doing it all in main, right, we basically had two separate blocks of code where we said, push loop for the stack of doubles, pop loop for the stack of doubles, and then another loop, right, with the stack of integers. Now we've just simplified that with a function. So one function that handles everything, regardless of what the actual stack objects look like. So we've just, further simplified things. So now we just have only a total of one push loop, right? And then only a total of one pop loop. functions. So that's our parameter list, and then that's where the body starts is here. But again, we've just simplified that whole process by not having to have, two separate push loops and two separate pop loops like we did before when we just had everything, kind of put together in main. So in this case, it's really good to not only template the class, right, which we already did that, but even templating this function is really helpful because now there's just kind of one version of everything, right? We don't have to write out multiple versions. So rather than either duplicating the code in main or rather than writing out two manually overloaded versions of test stack, we just keep things very generic and very simple through templating, right? Because the compiler will handle the details as far as creating the different versions of the test stack function based on the function calls that we make, right? So the first function call is going to create a version of the test stack where t is replaced by int, right? And then the second function call, or the first one's going to do the double one actually, and then the second function call is going to create the second version of the test stack function where t is replaced by int. And then with both function calls, we pass in the 5 parameters, right? The name of the object, the initial value, the value that we're incrementing by, the number of elements or the size of the stack, and then a string that represents the name of the stack. And then we did that down here as well. And then, so now we're able to do the same thing that we were doing before, but taking full advantage of templates, both on the class side and now also on the standalone function side as well. And so we have the same output really as before because we use the same number of elements and the same increment value and all that. But again, we've just kind of cleaned up our implementation a little bit further by not having to duplicate things. So it's better in this case to have the templated function rather than two separate blocks of everything in main, which is exactly what we did. So now we have the push loop, right, and then the pop loop. And then all we have to do is call the function 2 different times with the 2 different objects that we created. And now we're able to accomplish what we were doing before, right, but in a much more concise manner by taking advantage of function templates. that idea of stenciling out different versions, right? That applies with your functions similar to how it applies with the entire class itself. So the compiler's in essence, right, creating different overloaded versions of this function where T is being replaced, right, by the actual type of the stack object that's being passed in. So that's the basic idea of templating both at the class level and at the function level. And so then next, or really in 2 weeks when we meet next, we'll start looking at container classes in chapter 15, and we'll see how this idea of templating comes up once again as well, where the classes are templated, and then oftentimes the functions that we use to work with those classes, we're going to also want to have be templated as well. So we'll look at things like DQ, vector, and we'll also talk about iterators and how they are like pointers and can be used to iterate through your container. And one of the big realizations of that chapter is the fact that even though internally these different container classes, right, are physically implemented differently in memory, right? An array is stored contiguously in memory. A vector is stored contiguously in memory. A DQ is semi-contiguous because you have different chunks that are stored together, but the overall DQ is not all stored together. And then you have things like linked list, which are not stored at all together in memory, right? You can have all the nodes all over the place in memory. But the idea is that, again, we generalize a lot of these things, and we can use iterators to iterate through the structure. And the code for actually iterating through the structure is really the same regardless of what the type of the structure is, in terms of the actual code that we write out to do things like loop through the vector object or the list object or the forward list object. Even though the internal implementations are certainly different across some of those containers, the way that we actually iterate through them using iterators is really the same. So the standard library, you know, generalizes a lot of these major operations, such as iterating through a structure. So we'll talk about the container classes, and then we'll also talk about iterators and how they can be used to work with and process those different types of container classes. Okay, so we'll go ahead and